Hi there. These are the second part of the notes on orthogonality. Let's get started. This is review. If we want to find the dot product of two vectors, we multiply matching components, we add the results. And so the dot product of these two vectors, we multiply 3 times -4, and we get -12. Then we multiply 2 times 1, and we get 2. -12 plus 2, the answer is -10. If we want to find the exact angle between two vectors, we can use this formula. The dot product is almost the cosine except for a unit conversion. And then this part down here in the denominator corrects the units. So that both sides have the same lack of units, that both sides are now unitless and they're equal to each other. Still reviewing, a set of vectors is an orthogonal set if every pair of vectors in the set is orthogonal. Orthogonal means their dot product is 0. And if we have an orthogonal basis, then we can calculate the alternate coordinates in that basis using this formula instead of row reduction. V is the vector that we are converting. And U is one of the vectors that's in the basis. That can show up, it shows up 3 different times in this formula. The vector they're actually converting only shows up once. And we ended last time with this question: is it possible to take an ordinary basis and make it orthogonal so that we can use that dot product formula instead of row reduction? And the answer is yes. And today we're going to cover how. It's a process called the Gram-Schmidt process. If you're given any basis for a subspace, you can calculate an orthonormal basis for that subspace. We haven't defined what orthonormal means yet. We've only defined what orthogonal is. We'll get to this in a moment. The key step in the Gram-Schmidt process is the calculation of what's called the orthogonal projection. This isn't the entire process. This is the hard step in the process. And so let's walk through this step first. It's calculating what's called the projection of a vector onto a subspace. And you'll recognize this formula that we just saw a moment ago for converting a vector to an alternate basis. We convert these vectors into an alternate basis, but then build a linear combination with these basis vectors. So I calculate V in the alternate basis with respect to the first vector, with respect to the second vector, with respect to the third vector, and so on and so forth. And then build a linear combination taking those coefficients times the basis vectors. This is called the orthogonal projection of V onto W. And we'll give this a try. So let's start with these 3 vectors here. W is the span of these 2 vectors, U1 and U2. First thing we're going to do is check that U1 is perpendicular to U2. Okay, so the dot product of U1 and U2 is 2 times -2 plus 5 times 1 plus -1 times 1. This is -4. This is 5. And this is -1. -4 and -1 and +5 do add up to 0. And so we have checked that these 2 vectors are orthogonal to each other. And so now we're going to find the projection of V onto U1 and U2. So the projection of V onto W, which we abbreviate as V with a little pointy hat on it, here's the formula. We're going to calculate the component of V onto U1. So that's v dot u1 over u1 dot u1. This will be a number, and we'll take that number times this vector u1. So u1 shows up again in the formula. And then we'll do the same thing onto this other vector, v dot u2 over u2 dot u2. This will be a number. We'll take that number times u2. Add these together, this gives us a projection. So let's calculate this out. V dot u1 is 1 times 2 plus 5 times 2 plus negative 1 times 3. 12 minus 3 is 9. u1 dot u1 is just this vector dot with itself. That's 4 plus 25 plus 1 is 30. V dot u2, these two vectors, negative 2, and then positive 2, and then 3. This is 3. And u2 dot with itself is 4 plus 1 plus 1, which is 6. And so the projection of v onto w, or v with this pointy hat, is this dot product over this dot product, 9/30 times u1 plus 3/6 times this vector. We can simplify this a little bit. 9/30 reduces to 3/10 times 2, 5, negative 1. And 3/6 reduces to 1/2 times negative 2, 1, 1. 3/10 times 2, 5, negative 1 is 0.6, 1.5, and negative 0.3. 1/2 times negative 2, 1, 1 is negative 1, positive 0.5, positive 0.5. When we add these together, we get negative 0.4, 2, and 0.2. So this is the calculation for finding the projection. What is this calculation actually doing for us? What is this vector? So let me draw a small diagram because I didn't leave myself much room left. u1 and u2 are two vectors. They don't point in the same direction. They're linearly independent. And so their span is a plane. V is not on that plane. V is somewhere outside of that plane. But if I drop a perpendicular down from V to that plane and look at the line that is on the plane, the vector that is in the plane that is directly underneath V, that vector is called the projection. That's the projection vector that we're looking for. This vector is in this span. We know it's in the span because it's a linear combination of u1 and u2. And it's the span that forms a leg of a right triangle with V as the hypotenuse. Are we good? So here's why this works. I have this vector here, u, and this other vector v that is not on the line that u generates. And if I drop this perpendicular, the projection is the part that's directly underneath the projection, underneath the vector. And this is the vector that I want to calculate. Well, using the angle formula, we know that the dot product of v and u is the magnitude of v times the magnitude of u times the cosine of this angle theta that's between v and u. And using the same formula, the dot product of u and u is the magnitude of u times the magnitude of u times the cosine of the angle between u and u, which is 0. That's a 0, not a theta. Well, the two of the magnitudes of u's co-cancel, and cosine of theta is equal to 1, and so that doesn't change anything. So this expression simplifies to v cosine theta over u. But the cosine of theta is the adjacent side divided by the hypotenuse. The adjacent side is the magnitude of p, and the hypotenuse is the magnitude of v. And so if we replace cosine with magnitude of p over magnitude of v, then the v's cancel, and we get a fraction that is the magnitude of p over the magnitude of u. Hold on to this fraction. We're going to use this on the next slide. If we multiply the vector u by this fraction, then we get magnitude of p over magnitude of u times the vector u. But this is a unit vector. Dividing u by its magnitude scales this vector down to a length of 1. And then multiplying it by the magnitude of p then makes it same direction, but it's now a vector that's p units long in the direction of u, but that is the vector p. And that's the projection vector that we're looking for. So the formula that we've been covering finds this leg of the right triangle that's under v. What if instead of finding this leg, we want to find the vector that's perpendicular to u? How would we find this vector? Well, using the head to tail rule, if this vector is p, and this vector is v, and this vector is a vector that we want, let's call it r, then p plus r is equal to v, which means that r is the same thing as v minus p. So we'll take the vector that we have, we subtract the projection from it, and then we get, instead of the vector that's underneath v, we get the vector that's perpendicular, and we get the other leg of the triangle. So how do we do this? We do this by subtracting v minus p. And then that gets us the perpendicular vector instead. If you understood all of that, then you're ready to talk about the Gram-Schmidt process. Okay? So if we turn the projection around, make it negative, and then add it to v, we get the vector that's shown in blue. That vector forms an orthogonal set. So let's talk about the Gram-Schmidt process now. We're ready to take a look at this. We have any linearly independent set of vectors, and we want to construct an orthogonal set of vectors that spans v. We're going to leave the first vector in the set unchanged. The first vector, we're going to lock it in place and make the other vectors move relative to it. That is, if my vectors are not orthogonal, that angle is not 90 degrees, I'm going to choose to make that first vector lock in place, and I will take the second vector and I'll move it to a new position so that the angle is a 90-degree angle. That's the process. Okay? So the first vector is unchanged. And then every other vector, we first calculate the projection, and then we subtract v minus the projection. This is at v minus p, and that gives us the perpendicular side of the triangle instead of the base of the triangle. Okay? If we get some ugly fractions here, we can scale this vector by the lowest common denominator of the components. If you want to do that, that just makes the numbers a little bit easier. We just get a scaled version of the vector we want, but it's still perpendicular. Okay? So this is it. Leave the first vector unchanged, project every vector after that onto the vectors that come before it. So this is an easy step, nothing to do. This is a hard step. Let's work through an example. I want to find an orthogonal basis for the column space of A. So the column space of A is the span of these three columns. 3, 1, -1, 3, -5, 1, 5, 7, and 1, 1, -2, 8. Okay? So what we're going to do with the first basis vector is leave it alone. So the first vector does not change. For the second vector, we're going to calculate v2 hat, and then we're going to calculate v2 minus v2 hat. Okay? So v2 hat is v2 dot with the vector that came before it, which is v1, over v1 dot v1. This gives us our proportion, and then we dot that with v1. This will be v2 hat. All right. Let's calculate this fraction. v2 dot v1 is -5 times 3 is -15, plus 1 is -14, minus 5 is -19, -19 minus 21 is -40. v1 dot with itself is 9 plus 1 is 10, plus 1 is 11, plus 9 is 20. So we get -40 over 20 times v1. This is just -2, so -2 times this vector is -6, -2, +2, and -6. So we've calculated v2 hat, and now we're going to take v2 minus v2 hat. So -5 minus -6 is +1. 1 minus -2 is +3. 5 minus 2 is also +3. And -7 minus -6 is -1. We can check our work at this point. This vector should be orthogonal to v1. The goal is to form an orthogonal basis. And so this vector needs to be orthogonal to v1. But we can check that. 3 times 1 is 3. 1 times 3 is 3 again. That's 6. -1 times 3 is -3. 3 times -1 is -1. So we have 6 minus 6 is 0. And so these two vectors are orthogonal. So my orthogonal basis, this is my first vector, and this is the second vector in the orthogonal basis. And so we now have to do the third vector. We have to figure out what the third vector is. So again, there are two steps. We're going to calculate v3 hat, and then we're going to calculate v3 minus v3 hat. v3 hat is the projection of v3 onto both vectors that came before it. This vector and this vector. So it's v3 dot v1 over v1 dot v1 times v1 plus v3 dot with the new v2, not the original v2, All right, let's work through this. This fraction is the dot product of v3 with v1, so that's 3 plus 1 is 4, plus 2 is 6, plus 24 is 30. v1 dot with v1 is 9 plus 1 plus 1 plus 9 is 20. So we have 30 over 20 times 3, 1, negative 1, 3. And then the second fraction is v3 dot with the new v2, not this vector here, but this vector over here. So 1 times 1, 1 times 3, now we have 4. Negative 2 times 3 is negative 2. And then 8 times negative 1 is negative 10. And then this vector dot product with itself is 1 plus 9 plus 9 plus 1 is 20. Times 1, 3, 3, negative 1. So let's calculate this out. This is 1.5 times 3, so that's a 4.5 minus 0.5 is 4. 1.5 times 1 is 1.5 minus 1.5 is 0. Negative 1.5 minus 3.5, minus 1.5. Let's try that again. Negative 1.5 minus 1.5 is negative 3. And 4.5 and 0.5 is 5. 4, 0, negative 3, 5. And so we're ready to calculate v3 minus v3 hat. So that's this vector, 1, 1, negative 2, 8. Minus the projection vector, one minus 4 is negative 3. 1 minus 0 is 1. Negative 2 minus negative 3 is positive 1. And 8 minus 5 is 3. If we did this right, again, this vector here should be orthogonal to both of these other two vectors. This vector gives me, this dot product is negative 9 plus 1 minus 1 plus 9. So negative 9 and plus 1 is negative 8. Negative 8 minus 1 is negative 9. Negative 9 plus 9 is 0. And then this dot product should be 0 also. And so the question was to find an orthogonal basis for column space of A. We have that answer. Our basis is the first vector, which did not change, 3, 1, -1, 3. And then our repositioned second vector, 1, 3, 3, -1. And our third vector, -3, 1, 1, 3. All right, so we've done this. We found an orthogonal basis for the column space. The first vector doesn't change. The second vector projects onto just V1. The third vector projects onto V1 and V2. All right. Let's throw in a definition here. An orthonormal basis is not just an orthogonal basis. It's a basis in which every pair of vectors is orthogonal, and all vectors have a length of 1. They're all unit vectors. So it's an orthogonal basis made up of unit vectors. Last time we saw that these three vectors were an orthogonal set. Construct an orthonormal basis from them. So what I need to know is what are the magnitudes of these vectors. This vector has a magnitude of the square root of 11. This is 9 plus 1 plus 1. This vector has a magnitude of the square root of 1 squared plus 2 squared plus 1 squared is square root of 6. This is going to be the ugly one. Magnitude of V3 is the square root of 1/2 squared plus 2 squared plus 7/2 squared is 1/4, and 49/4 is 25 halves plus 8 halves is 33 halves. And so if we want an orthonormal basis instead of just an orthogonal basis, this word normal means make them to unit vectors. We just have to divide each of these vectors by those magnitudes. And so we get an ugly looking answer, but this is the answer. Our basis is, the first vector is 3 over square root of 11, 1 over the square root of 11, and 1 over the square root of 11. The second vector is -1 over root 6, 2 over root 6, and 1 over root 6. And then the third vector is -1/2 divided by the square root of 33 halves. And this is something we can definitely simplify. -2 divided by the square root of 33 halves, and 7/2 divided by the square root of 33 halves. I'm not going to take the time to simplify that, but we could simplify if we wanted to. Okay? In other words, Gram-Schmidt will get us to an orthogonal set, and then if the question asks for an orthonormal set, we just divide every vector by its magnitude, and then we're done with that. In the notes, if you look at steps 3 and 4, steps 3 and 4 take Gram-Schmidt a little bit further and make it into an orthonormal basis. All right, so let's work through a long example. This is an example with 4 vectors, and we want to find an orthonormal basis for this span. Okay, so we're going to call these vectors V1, V2, V3, and V4. And the first vector, we're going to leave it unchanged. We're just going to let W1 and V1 be the same vector. So then the second vector gets projected onto W1, which is the first vector. So we take the dot product of these two vectors, that's -400, divided by the dot product of this vector with itself, that's +400. Negative 400 over 400 is just negative 1 times W1. And so V2 hat is positive 10, negative 2, positive 6, negative 16, negative 2. And then W2 is V2 minus V2 hat. 13 minus 10 is 3. 1 minus negative 2 is 3. 3 minus 6 is negative 3, and so on and so forth. We can check this vector has to be orthogonal to this vector, the vector that came before it. Okay? So that's the second vector. This is written out in your notes, so I'm going to move on. The third vector, this one here, we're going to project onto the first vector and the second vector. So it's the dot product of these two vectors, V3 and V1, over the dot product of V1 with itself. So that's negative 200 over 400 times W1. And then the dot product of this vector and not the original V2, but the replacement, which in the notes I'm calling W2, the replacement for the second vector. We're going to dot product those two vectors together, divided by W2 with itself. We get negative 48 over 36 W2. And when you add these two vectors together, this is V3 hat. V3 minus V3 hat gives me this vector here. This is going to be the replacement for the third vector. So we kept the first vector exactly the same. We replaced the second vector. We replaced the third vector. And now we're about to replace the fourth vector. The fourth vector projects onto the original first vector, the replacement second vector, and the replacement third vector. Replace all of the vectors that we've constructed up to this point. When we calculate these dot products and these fractions, we get 200 over 400, negative 36 over 36, and negative 54 over 108. We take that linear combination of the three vectors, we get negative 11, negative 2, negative 3, 5, negative 2. When we take V4 minus V4 hat, this is a replacement for V4. So now V4 is gone and it's being replaced by this vector. All right. I'm going quickly through this because the calculations are very repetitive for a 4-element basis. So we started with these three vectors. We ended up with these four vectors. We ended up with these four vectors. The first vector didn't change, but every vector after that got replaced. We have an orthogonal basis, but not an orthonormal basis. So if we want to make this into an orthonormal basis, we have to calculate the magnitude of each of these vectors. The magnitude of W1 turns out to be the square root of 10 squared plus 2 squared plus 6 squared plus 16 squared plus 2 squared is the square root of 400, which is just 20. The magnitude of W2 is the square root of 9 plus 9 plus 9 plus 9, square root of 36. But that just equals 6. The square root of W3, or the magnitude of W3, sorry, is the square root of 36 plus 36 plus 36 is 108. And that turns out to be 6 root 3. And the last one, the magnitude of W4, is the square root of 25 plus 25 is the square root of 50, which is 5 root 2. When we divide by each of these vectors, we get our final answer that our orthonormal basis, the first vector, will be divided by 20. So negative 10 over 20 is negative 1/2. 2 over 20 is 1/10. Negative 6 over 20 is negative 3/10. 16 over 20 is 4/5. And 2 over 20 is 1/10 again. These vectors get divided by 6. So we get 1/2, 1/2, negative 1/2, 0, 1/2. These vectors get divided by 6 root 3. So we get root 3, 0, root 3, root 3, and 0. And then this vector here gets divided by 5 root 2. So we get 0, root 2, 0, 0, negative root 2. All right. These should be 1 over root 3, 1 over root 3, 1 over root 3, 1 over root 2, negative 1 over root 2. The square roots are in the denominators here, not in the numerators. Sorry about that. Okay? All right. Let's move on. Let's find an orthonormal basis for this span here. We're going to do this problem start to finish. It's just 2 vectors, so it won't take us too long. The first thing we're going to do is leave this vector alone. So v1 will stay at 3, negative 4, 0. But the second vector, we have to do 2 steps. We have to calculate v2 hat, and then we calculate v2 minus v2 hat. So v2 hat is v2 dot v1 over v1 dot v1 times v1. v2 dot v1 is 3 minus 8 is negative 5. v1 dot v1 is 9 plus 16 is 25. Times 3, negative 4, 0. This is negative 1/5. So we get negative 3/5, which is negative 0.6. And positive 4/5, which is 0.8 and 0. v2 minus this will be the vector 1.6. 2 minus 0.8 is 1.2, and 2 minus 0 is 2. And so our orthogonal basis is 3, negative 4, 0, and 1.6, 1.2, and 2. But the problem is asking for an orthonormal basis. Normal means unit vectors. And so we need to calculate some magnitudes here. The magnitude of the first vector, 3, negative 4, 0, is the square root of 25, which is 5. This other one's going to be a little bit of work here. 1.6, 1.2, and 2 is going to be the square root of 1.6 squared plus 1.2 squared plus 2 squared, which turns out to be exactly the square root of 8, or 2 root 2. And so for an orthonormal basis, the first vector gets divided by 5, so we get 3/5 negative 4/5, and 0. The second vector gets divided by 2 square root of 2. And that gives me this basis here scaled down to unit vectors. All right. This is a different type of question. Let's take a look at this one. These two vectors generate a plane. And this vector does not lie in that plane. So V is somewhere up here. Find the distance from V to P. Well, the distance is just the magnitude of the perpendicular vector. So the distance, the base vector is V hat. The perpendicular vector is V minus V hat. But we just want the distance, so we just need the magnitude of that vector. That's the idea. Okay? So what I'm going to remind you is that in the previous problem, we found this orthogonal basis. Three, negative 4, 0, and 1.6, 1.2, and 2. Now back up for just a second. That's this basis that we found right here. Okay? We can calculate the distance from V to P by projecting V onto this orthogonal basis. So let's do that. The projection of V onto this orthogonal basis is V dot V1 over V1 dot V1 times V1 plus V dot V2 over V2 dot V2 times V2. All right, so 2, negative 1, 3 times 3, negative 4, 0. This dot product is going to be 6 plus 4 plus 0 is 10 over 25 times 3, negative 4, 0. And then this one's going to be a little bit messier. 2 times 1.6 is 3.2 minus 1.2 is 2. 2 plus 6 is 8. Over this vector dot product itself turns out to also be 8. Times 1.6, 1.2, and 2. Let's see. So 10 over 25 is 2/5. 2/5 times 3 is 6/5. That's 1.2. 2/5 times negative 4 is 8/5. That's negative 1.6. 2/5 times 0 is 0. 8 over 8 is 1. So this is 1.6, 1.2, and 2. When we add these together, we get 2.8. Negative 1.6 plus 1.2 is negative 0.4. And 0 and 2 is 2. All right. This is the projection. That's this vector down here. But we want the perpendicular vector, the one that's up here. That's V minus V hat. So 2 minus 2.8 is negative 0.8. -1 minus -0.4 is -0.6. And 3 minus 2 is 1. And the last thing we need to do is take the magnitude of that vector, which is the square root of 0.8 squared plus 0.6 squared plus 1 squared, which turns out to be exactly the square root of 2. And so how far is this vector up here from the plane? This turns out to be square root of 2. Okay? So we've done a fair number of examples here of finding these projections, calculating orthogonal and orthonormal bases, and finding the distance from a point to a plane. Okay? We have one more part to go to finish up the orthogonality unit. We'll look at those in a couple of days. Take care. I'll see you.